Okay, this video is on infinite geometric series, and this is quite a bit more interesting than other things. Let's just have a look at something. Let's rewrite down the formula for the sum of a geometric series. So let's just have a look at it. Is a r to the n minus 1 over r minus 1. Okay, now if we choose, or if we happen to have an r, a value of r, the ratio, which is between 1 and negative 1, okay, let's just have a look at what happens if r's, no, so let's just say if r is equal to 0.7 or something, it's less than 1, okay, what happens to r to the power n? So let's just have a look at this bit in here. What happens to that as n gets bigger and bigger and bigger and bigger? Okay, so just looking at 0.7, so we're multiplying 0.7 by itself over and over and over again. So what happens to that? I'll just go to the calculator. So I've got 0.7, okay, and if I multiply that by itself, so multiplying by 0.7, we get 0.49. If I multiply it by itself again, we get 0.343. If we keep doing that, can you see how the number gets smaller and smaller and smaller? And in fact, if I keep just pressing enter over and over and over again, that number gets really, really, really small. And in fact, as the calculator is starting to freak out a little bit because these numbers are getting super small. In fact, what happens is that as n goes to infinity, as n gets really, really big, r to the power n gets closer and closer to 0. And this is a really important result because what we can then say is, looking at this formula for the sum of a geometric series, that the sum as n goes to infinity is equal to, alright, so let's have a look at this, a, now r to the n will go to 0, it becomes 0, it gets closer and closer and closer to 0, so it will be 0 minus 1 over r minus 1, okay, and 0 minus 1 is just negative 1, negative 1 times a is negative a over r minus 1. There we go. We'll just clean this up because we don't like the negative. Let's just times everything by a negative. We'll just get a on the top line. If we times this bottom line by negative 1, we'll get 1 minus r. And so that is your formula for your infinite sum of a geometric series if and only if r is between 1 and negative 1. That only happens for those values of r, because if r is bigger than 1, so let's say 2, then 2 to the power n, that's just going to get bigger and bigger. 2 squared, 2 cubed, 2 that's going to get bigger and bigger and bigger. It's only if r is between 1 and negative 1, so make sure you only use this when r is between 1 and negative 1. Let's have a look at an example. Okay, example. Find the infinite sum of 4, 2, 1, half, etc., etc. Find out, as this gets bigger and bigger, what this goes to. Let's just write down all our values first. What's our initial first term is 4. What's our ratio? What's everything getting times by? It's getting times by a half at every step, getting multiplied by half. Okay, and we'll just leave it there for a second. What I'll do first is I'm just going to use our old formula. So Sn is equal to a r to the n minus 1 over r minus 1. What I want to just do is calculate a few values and show you what happens. So let's do S3 is equal to, let's do S10, and let's do S100. Just see what happens. And so I might just go straight to the calculator and do this, but S3 will be equal to, so if n is equal to 3, we'll have 4 times r to the power n. R is half, so half to the power n, which is 3, minus 1, I'll put brackets all around that, over r minus 1, So half minus 1. I'm going to go to the calculator, and when I do S3, S10 and S100, all I'm changing is n, so I'm just going to change this value every time on the calculator and just see what happens as n gets bigger and bigger. Okay, so let's go to the calculator. Oh, I just have to remember it, because it's 4 half to the power 3. Put the fraction first. What was it? It was 4 times, brackets. The ratio was a half, so I'll put it in as a decimal. It's a bit easier to see. So now I've screwed that up. Oh no, what's it done? Get rid of that. 0.5 to the power of 3 minus 1 over, I can't remember what I had, half minus 1, which is negative half. So negative 0.5. And so that will be, I'll just make that case right there. This is going to be the sum of the first 3 values. And what is it? It's 7. Okay. Let's go up, and I'll just change this by pushing up and pressing enter. That brings it into my new thing as an exact copy. And I'm just going to change the value of n. Let's change that to 10. The power of 10. And let's see what the sum of the first 10 digits is. It's 7.99219. Okay, so that's after 10 digits. Okay, let's do it after 100 digits now. Okay, so again, I'll go up, I'll press enter, just copy it in, and I'm going to change that 10 to 100. What's it going to be? Now the calculator is saying 8, it's approximating it to 8. Maybe I'll go and do 50, okay, if n's equal to 50, because the calculator, maybe I'll even do less than 50, I might do 30 or something like that. And what you see is that it converges. We say that it converges. No, it's still saying 8. What it's doing is the sum is getting closer and closer and closer to the number 8, okay? So S10 was equal to, S3 was equal to something around 7. That was equal to 7.9987 or something like that. S100 would have been like 7.999999, something like that, getting closer. And what that means, as this number gets bigger, this number gets closer and closer to 8. Let's have a look at this. Our formula before, our infinite sum of any geometric series that has a ratio which is in between 1 and negative 1 was equal to a over 1 minus r, which is a, which is 4, over 1 minus, what was the ratio? Half, which is 4 over 1 minus a half is a half. 4 divided by half is 8. And so there is your infinite sum. This number gets closer and closer. We say that it converges to this number here. It gets closer and closer and closer. And that's basically all there is to infinite sums. That's a bit more exciting, a bit more enjoyable. And you'll see why, is that if you think about this, 4 plus 2 is 6, 6 plus 1 is 7, half, 7 and a half, these numbers get smaller and smaller and smaller here, so they don't make very much difference. As you get to the big numbers of values of n, these numbers just become so small they're insignificant, and it never ever gets to 8, but if you go right up to infinity, it just gets to 8. Hope that's all good. I'll see you in class.